Welcome back to the circular motion lesson. In the last video, we had just finished off finding our speed of the Earth in terms of its orbit around the Sun, in terms of meters per second, but now we're actually going to work on converting this value into kilometers per hour. So this will be step number 2. So I'm going to take my value, and I'm going to basically write this so it's ready for unit analysis. So I'm going to write my meters on the top, and then my seconds I want to write down on the bottom. And then I'm just going to create some fractions just to cancel out my units. It doesn't matter which one you go with first, as long as essentially they're in there correctly. So here we're trying to get rid of meters. So I want my meters on the bottom, and I'm trying to introduce kilometers, so that goes on top. And I know that in 1 kilometer, there is 1,000 meters. And we can also do this in the same step where we're converting our seconds into hours. So I know that in 1 hour, which I'm going to put on the bottom here, and seconds goes on top to cancel those units, I know that there are 3,600 seconds in 1 hour. So to plunk this into my calculator, I'm going to go 2.99 times 10 to the 4. This 1,000 here is in the bottom, which means I'm going to divide by 1,000, and then I'm going to multiply by 3,600. So if you put this into your calculator, you should get 107,640 kilometers per hour. And once again, we do need to count for sig figs here. So here we had 3 sig figs in our previous answer. So our value is also, or our next answer is going to have 3 sig figs as well. So that actually here rounds up to 108,000 kilometers per hour. And if we want to put that into sig figs, or sorry, scientific notation, that is 1.08 times 10 to the power of 5 kilometers per hour. And remember, just to get this exponent here, it's just based on how many times you've moved that decimal point. And so here it would have been 5. So now that we're all done here, we can finish off this question by writing a sentence. So we can say the speed of Earth is 2.99 times 10 to the 4 meters per second, or 1.08 times 10 to the 5 kilometers per hour. Okay. So just as a little note here, so the speed of a planet as it rotates on its axis can be determined in the same way, but varies depending on the latitude at which it's spinning. We're actually going to look at this topic a little bit later on in the unit, but we're not going to worry about it right now. So let's just do a couple of examples, just practicing what we just learned about the speed of circular motion. So we're going to look at example number 1. So a pebble is stuck in the treads of a tire at a distance of 36.0 centimeters from the axle. It takes just 0.40 seconds for the wheel to make 1 revolution. So we want to know, what is the speed at any instant? Alright, so once again, just like the previous video, we are going to look, or the previous example, we are going to first write down our information. So here it says the pebble is stuck at a distance of 36.0 centimeters from the axle. So this here actually tells us the radius of this motion. So it's 36.0 centimeters. One thing that, as I mentioned in the previous video, we typically work with meters per second, so we're actually going to convert this. So to convert centimeters to meters, I'm going to divide by 100, which gives us 0.360 meters. Make sure you include that 0 in there because we have to keep track of our sig figs here, so do not forget that. And then we're given the time it takes for 1 revolution. So if we're trying to calculate that period, remember it is the amount or the number of seconds it takes for 1 cycle. So it is 0.40 seconds for 1 cycle. And which we can even just simply put as 0.40 seconds. So now we can go ahead and plug this into our speed equation, which is 2 pi r divided by your period. So we have 2 times pi times your radius, which is 0.360 divided by your period, which we know is 0.40. So go ahead and plug that into your calculator, and we should get a value of 5.6549. And we'll just keep track of sig figs here. So here we have 3 sig figs in our radius, but we only have 2 in our period. And using that dividing rule, we have to use the least number of sig figs. So our answer here should have 2 sig figs. So our speed is 5.7, and our units here are going to be meters per second. And once again, we just need to write a sentence just to finish off this question. So the speed of the pebble is 5.7 meters per second. All right, let's move on to example number 2. So in the women's Olympic hammer throw, a hammer consists of a 4.0 kilogram metal ball attached to a thin wire of negligible mass. While grasping the handle in her hands, an athlete spins in circles, then releases the hammer in order to propel it the greatest distance. On a certain throw, the hammer is spun in a 2.4 meter radius circular path and released with a horizontal velocity of 20 meters per second at a height of 1.0 meters. So part A wants to know, what is the horizontal distance the hammer will travel? So this one here is actually going to be a bit of a throwback question to Unit 1, where we're talking about projectile motion. So just to draw a little scenario or a little picture of what's going on here. So we know that this hammer is being thrown from a vertical height of 1.0 meters, and it's being released at a horizontal velocity of 20 meters per second. So it's getting launched at this height, and eventually the gravity is going to bring it down, and it's going to hit the ground. And it's going to give us this total horizontal distance, which I'm going to call delta D. And we're just going to put a little h here just to represent it's the horizontal distance, not the vertical distance. So when we're looking for our horizontal distance, and we know that we have a horizontal speed of 20 meters per second, we can actually use one of our formulas in order to find our change in our distance. So with speed, that is equal to your change in your distance over that change in time. So that's actually we're going to work with both of these variables here, so speed and our change in distance. But the one kind of catch here is that we don't have our time. And so in order to find our time, we actually need to be working with this vertical component here, which so far all that we really know right now is we have a total vertical height of 1.0 meters. So going back to Unit 1, we should always write down kind of the information that we know. So I'm just going to write down our vertical information down here. So I know right off the bat here I have a change in height, or that change in distance, is 1.0 meters. And now there's some other stuff that you may or may not know, or I guess may have forgotten that you know from our first unit. You know that the gravity pulling down that metal ball is gravity, which is 9.81 meters per second squared. And then one last little bit of information that we know is that if we're launching this hammer at a at a horizontal speed, we know that there's no vertical initial speed. So we could say that the initial speed is 0 meters per second. Then we can use one of our kinematic equations from our first unit to solve for time. So let's find time. So look at your equation. We are going to use delta D is equal to your initial velocity times the change in time plus 1/2 times your acceleration times the time squared. Hopefully that rings some bell from the first unit. So now we're going to plug in all information. We know that the change in distance was 1.0. The initial velocity was 0 times your change in time, plus 1/2 times your acceleration, which is 9.81, and times that change in time, which we don't know. So I'm just going to go ahead and first simplify this equation here. We have 1.0 is equal to 0 times anything is just 0, so I'm not even going to include that. But I can simplify this 1/2 times 9.81, which is 4.905, and then delta t squared. Next, I want to get this delta t squared by itself, so I'm going to get rid of this 4.905. And to do that, I'm going to divide. So when we go 1.0 divided by 4.905, we would get, and this will be a slightly rounded value here, so we have 0.2039. That's equal to delta t squared. So we're not quite done yet. We need to get delta t, so we have to get rid of this squared value. So you're going to square root both sides. And once we're done that, you're going to plug this into your calculator, and we should get that our change in time is equal to 0.45 seconds. And this one here is a rounded value. I'm just sticking along with our sig figs here. So if you want me to go back and just do a quick explanation of that, we don't have to worry about sig figs in terms of our acceleration. We really only have to work with this measured distance, which is that change in distance. So here, our value here had 2 sig figs, so our answer should have 2 sig figs as well, which is how we get 45 seconds. Alright, so now we have our change in time, which means that we can go ahead and use this equation. We have the horizontal speed, we know how long it takes for it to reach from the top to the bottom, and so now we can find that horizontal distance. And I'm just going to be awkward, I'm going to write this down in part B here, but hopefully you should still have some room in your notes for your question. Alright, so part 2 here. So we have speed is equal to your delta d over delta t. So plugging what I know that we had that horizontal speed of 20. We're looking for that displacement, or that distance, sorry, and our time as we had up here was 0.45. If I write this 20 over 1, then I can cross multiply to solve. So 20 times 0.45 would give us 9.0 meters for our total horizontal distance. So here we have 2 sig figs. We're just using the multiplying rule. We have 2 sig figs times 2 sig figs means that our answer is going to have 2 sig figs here as well. So don't forget that decimal 0, please. And so now, just to finish off part A, we are going to write a sentence. So the horizontal distance the hammer will travel is 9.0 meters. And I guess just to quickly go back, if you kind of forgot about this part from Unit 1, the reason why we could use this initial velocity for the for the horizontal velocity is just because at the physics 30 level we don't consider things like anything slowing down in terms of the horizontal speed, in terms of like any like friction or anything. So we want to keep it nice and simple. So we just assume that there's no horizontal factors affecting that, which is why we can use this initial horizontal velocity as just the overall speed. Okay. But unfortunately, once again, I don't know how I keep doing this, but I need another video that is going to take up probably a whopping 5 minutes. So I will see you in the next video.